Hi, we're doing the notes for Chapter 3, Section 3 on linear combination situations. And a couple things we want to go through in today's notes. First thing is just talk about what is linear combination. And I kind of wrote that first word linear a little bit weird, but the point is I'm trying to point out that when they talk about linear combination, it's really just what's an equation for a line, what's going to give us a straight object as opposed to a parabola or some sine wave or some curvy thing or something. So if you're looking at an equation, want to figure out if it's linear combination, I tried coming up with what are the fewest number of rules I could have that would kind of meet any problem. And these will work pretty well, I think. I came up with two. And first thing is that all variables must be to the first power. So if you have like a x squared or a y to the third or square root of something, or to find out that square roots are actually exponents, you know it's not going to be a line. So all variables must be the first power. Second one is no variables are multiplied by each other. So you can't have an x times a y. So no variables are multiplied by each other. Or in other words, you can't have a variable times a variable. So for these, practice, you could, if you wanted to, pause the video, quick write them all down. You could just quick write them all down, or you could just kind of follow along. It's up to you. But just want to kind of point out what are some places where people make mistakes. So this first one, y equals 3x plus 4. Hopefully you look at that and you're like, it's a line equation, I recognize it, it's slope-intercept form. But if you go through and try to look at these two things, are all variables, any variables not to the first power? So all variables must be the first power. We have a y to the first, we have x to the first, we're good there. Do you have an x times a y? Nope. So then this one here must be linear. If you graph that thing, it's going to be a line. Now this one here, looks a little bit different, but you go through and check those two things again. Are all variables to the first power? Yep, we have a y to the first, we have an x to the first. Do you have a variable times a variable? Nope, nowhere do you have x times y, so this one also is linear. And left a little space there, because what you could do, I'll try to squeeze it in here, as long as you do the same operation to all of both sides, it's still equal. So this is the same as y equals 2.5x minus 1. So it's another example of the slope-intercept form. Okay, so first one, we did that. Second one, we did that. Now this third one, 2x minus 3y equals 7. So that's an equation we're not used to seeing, but go back to your rules. Are all variables to the first power? Yep, we have x to the first and a y to the first. You don't have x times y, so this one also is going to be linear. We're actually going to talk about these in the next section. We're talking about standard form for a line. This is an example of standard form for a line. Okay, here, all variables to the first power. We have a y to the first, we have this x squared. So for this one, it's not linear. It's not a line. This one here, we have x to the first and y to the first, but it disobeys the second rule. We have an x times a y, so this one also is not linear. And last example here, 2m minus 4n, wanted to throw in variables other than x and y. But if you go back to our rules, both variables are to the first power. We don't have a variable times a variable, so this one is going to be linear as well. Okay, so the next section is going to be discrete domains and continuous domains. It'll be Roman numeral 2 and Roman numeral 3. We're looking just at lines in this chapter, but discrete domains, what that means is that only certain values are going to work for x and or y. So only certain values work for x and or y. So the domain, the x values, or the range, the y values are going to be limited. And if you think back to the example we're going to use is, well, maybe I'll do this point first. When you actually go and graph this, the graph is made up of dots. So the graph is going to be made up of dots. If you think back to our notes from Chapter 3, Section 1, talked about Claire the car salesman. We said that Claire made $250 for every car she sold. X is the number of cars. Plus we gave her $30,000 for base pay. And if we were to go through and make a quick graph and see what that's going to look like, I'll maybe have her sell 0, 1, 2, 3, 4, 5, 6, 7, 8. So your graph doesn't have to look exactly like mine, but you might want to do a decent effort to it. We'll have her start out at 30,000, and maybe we'll go up to, well, we say 33,000. So we have 31,000 right about there, 32,000 right about there. Now our y-intercept for our graph is going to be the 30,000. So if Claire sells 0 cars, she's right there on the pay scale. Here we have 31,000, so 1 car adds 250, so it's a quarter of the way up to my next tick mark. 2 cars, she makes $500 more, so she'll be about halfway up. 3 cars would be 3/4 of the way up. 4 cars, she's at 31,000 now. And then you could add in a 5, a 6, a 7, and at 8, she's at 32,000. So you see, if drawn perfectly, the points would all be in a straight line. But that's going to be the discrete domain. And the reason is, you couldn't sell half of a car unless Claire works at a junkyard or something like that. She either sells 0 cars or 1. There's nothing in between that she could sell. Those would be the discrete domains. Continuous domains are going to be normal, so I don't have as much to say about that. So Roman numeral 3, continuous domains. And for these, any value is going to work for x and or y. So all values work for x and or y. Or you could say the domain and the range would be all real numbers. So the graph is just going to be a line. So graph is a line. In this chapter, at least, this chapter is linear. It's all about lines, so the graph is going to be a line. It is possible to have continuous domains for parabolas and sine waves and square root functions and all that as well. But the point is, you're not going to have dots. It's all going to be connected. The very last thing is actually jumping into kind of the next chapter a little bit, or next section. The next section talks about standard form for a line. And I just want to hit it briefly here because we have some of this in the notes. Let me jump and see what I have. So standard form for a line. Standard form looks like this. So it's ax, so I'm going to write a capital A times x, my variable, plus by equals c. And these are what I pointed out earlier when we were looking at the linear combination stuff. But the point is, we're going to have a number times x, and then we have a number times y. That would be the x coefficient and the y coefficient. And then c, in a lot of the cases, is going to be the total. So when you have a story problem that's saying what's the total number of points, what's the total amount of acid, that sort of stuff, often it's going to be in this sort of form. I just want to do 2 examples that'll help you navigate the problems in the homework tonight before we get the official notes on this section. So example 1, you could pause the video, quick copy down 1 and 2, or you could just kind of pay attention. It's up to you. But example 1, to determine a team standing in a hockey league, a team receives 2 points for every win and 1 point for every tie. Write an equation to determine the number of points a team has. So we want to go through first of all and figure out what are the variables. And one is going to be the number of wins that they have. One is going to be the number of ties. So I'm maybe just going to have that be W and T. And if we go to our standard form, it's AX plus BY equals C. If this was on the test, the point that would help you figure out this equation would be write an equation to determine the number of points. I didn't phrase it as the total points, but that's the same sort of thing. So what C is going to be is it's going to be the points. Or where are they in the standings? What's their rating in the standings? So then you have to figure out, okay, if this is going to be W, what number is paired up with W? Well, for every win they get 2 points, so it's a 2W. So if you have 1 win, you get 2 points. If you have 4 wins, you have 8 points. 2 times 4 is 8. And then y, our other variable, is going to be the number of ties. And I probably could put in like a 1t, something like that, because you have 1 point for every tie, but then it's not simplified. So I'm going to maybe leave that off and just say 2w plus t equals the number of points. The second one, our book likes doing ones like this. Write an equation to determine the total acid contained in a mixture that is X ounces of a 35% acid solution and Y ounces of a 60% acid solution. So it's real tempting. A lot of people just want to say, well, if I have X and Y, X plus Y equals my total. And that's true. X plus Y gives you how many gallons or how many ounces it is of the mixture you have, but not all those ounces are acid, because the acid is diluted. It's not pure. So if we go back to our AX plus BY equals C, well, C is going to be the total acid. Maybe I should over here finish this one off and say, all right, X plus Y equals total ounces. You'll see something like that in the homework. But if you're talking total acid, well, if we have X ounces, how many of those X ounces are actually acid? Well, it says we have a 35% acid solution. So you have to figure out, what do you do to your number of ounces to get just the acid? Well, if it's 35%, you always take and move your decimal 2 places when you're dealing with percents. So it's going to be a 0.35. So 0.35x. Now if I have 10 ounces of this solution, I know that 0.35 times 10 is going to give me the amount of acid. 3.5 ounces of pure acid are in that. Now over here for my 60%, I have my Y ounces, but only 60% of those Y ounces are acid. So again, you do 2 hops with a decimal. So you have 0.60 or 0.6 times Y. So 0.35x plus 0.6y equals the total amount of acid in the mixture. That's all I have to say about section 3.